exergonic reaction. So in an exergonic reaction, who has more energy, reactants or products?
Reactants.
So I'm going to put my reactants here. And then I'm going to put my products over here. And notice this is what we would call a reaction time course. I'm just looking at the chemistry over time and the conversion of reactants to products. I won't worry about the equilibrium constants or anything like that. It doesn't really matter. Now, you can see that over time, the energy changes. And this distant difference between reactants and products right here, that's my delta G. And it's negative because products minus reactants is going to give me a negative number. If this is 5 kilocalories and this is 20 kilocalories, my delta G is a negative 15, because 5 minus 20 is negative 15. But what's interesting is that when you look at this reaction, it doesn't proceed like this. There isn't this gradual loss in energy. The reaction time course, if you will, actually looks like this. There's an increase in energy, and then you get the conversion. Okay, you all right with that? And this hump here doesn't affect the chemistry. It doesn't affect the delta G, because if you add a little bit of energy, what do? You get it right back. So this business right here, that doesn't affect the energy budget of the reaction, right? Because while I add it, I get it right back. Okay. So we call this energy here. It's like, oh, this would release energy as it rolls down the hill, but first I got to get it to the top of the hill, so it'll roll down the hill. So this difference right here, the amount of energy you have to add to prime a reaction or get it going or whatever, it's called the activation energy or the energy of activation. We abbreviate it E sub A. And that is characteristic for every chemical reaction on the planet. So every reaction, while it has its own characteristic KEQ, it's also got its own characteristic activation energy. Some of them it's a lot, some of it's not very much. But even the most spontaneous reactions, like combustion of alcohol, still requires a little input of energy, right, for that to occur. So even though that's incredibly exergonic and releases large amounts of energy, it won't happen until you prime it, until you get it started. You get that energy right back, but you have to get it started. And that's called the activation energy. Now what the activation energy affects is the time it takes to get to the products. So it doesn't affect the ratio or the delta G, it affects how long does it take to get to the product. The higher the activation energy, the longer this takes. It takes longer time to add more energy. The lower the activation energy, the faster it goes. Now I'm going to give you a little bit of chemistry speak here. Again, don't tell your chemists because it's probably entirely not true. You reach a point right here where you have at this peak of this activation energy where you're in the middle of a reaction, right? You're in the middle of converting reactants into products. So then that means that it's neither a reactant nor a product at that point, right? Okay. It's in transition. In chemistry speak, they would call this thing, you may have heard this, it depends on how much chemistry you have, but we would call this thing a transition state species. It is not a reactant, it is not a product, it is intermediate, but it does have a higher energy content than the reactants. And that's the important part right there. Okay. Is this reaction exergonic or endergonic? Exergonic, right? Negative delta G. What would it look like if we wanted to put the endergonic one on?